Oh, good morning. Let's see. I'm going to be posting a video on the lab for this week, which is, it'll be probably due next Thursday or so. But for this lab, it's one on measuring velocity and acceleration by measuring distances something moves over and timing it and things like that. And I've gathered all the data already, and I'll give you a version of the lab that has the data filled in, and then you need to do some fairly elementary calculations, but I show you in the video that I'll post with it just how you do that. And so that'll be showing up here later today. I just made the video this morning. Actually made it twice because I forgot to change the viewpoint on one of them, and I'm lecturing over something that you can't even see. So that's what happened. So for today, I'm going to dive into, what screen do I have that thing showing on? Okay, screen 2, I guess. Yeah, and I'll just use that. Okay, so hopefully now maybe you see a pen sitting there on a piece of paper. If not, holler, but that should be what it is. Today we're going to start looking at projectile motion. Yesterday we got just a little bit of an introduction into that, into some right angle trigonometry that you're going to use for it. But the idea with the projectile, again, is that it'll be launched at some angle from the horizontal, and that's where we measure the angle from on this. And so this would be V0, the velocity. And we can calculate, imagine making a right triangle here, and it'll have an X component and a Y component. And so I think in your book they may use X hats and Y hats for this, but anyway, this part down here would be V0X, and we can think of it as an arrow if we want, or V0Y is going to be that part. But something that we'll use in all of our projectile motion problems is that the magnitude of this divided by the magnitude of that, V0X over V0, that's supposed to be an X, is going to be the cosine of that angle. And then V0Y over V0, this is the side opposite that angle divided by the hypotenuse. By definition, that is the sine of whatever the angle happens to be. And we almost always immediately solve these, or we just remember them this way. V0X will equal V0 cosine of theta, and V0Y will equal V0 sine theta. So these are called the components of the velocity. We could write the velocity as this vector plus this vector. And so those are components of the velocity. And splitting things into components is something that we'll be doing several times in different areas through the rest of the quarter. Now, the way that we apply this to projectile motion depends on a property of vectors that I didn't mention yesterday. And let's see, here's what that property happens to be. Let's suppose that we have a vector A, and we can write A as an X component plus a Y component. So we could talk about an X component of X, anyway, being a vector like this, and then a Y component of X looking like this. And let's see, do I need to introduce the idea of unit vectors? Maybe I'll resist that temptation. But then suppose we have a vector B that I can write as b sub x, a part that points in the x direction, plus a part that points in the y direction. And so I have that. Now, if the vector A is equal to the vector B, what that means is A and B have the same magnitude and they point in the same direction. So if this is A and this is B, they're parallel to each other, which means they point in the same direction. By the way, it doesn't matter if the vectors are sitting right on top of each other, or if I take this vector B and move it all the way over here, if they have the same magnitude and point in the same direction, we say that they're equal. But if that's the case, then this is the other property of the vectors. It means that A sub x will equal B sub x, and A sub y is equal to B sub y. And sometimes we can write these things in terms of, we can convert these vector equations into scalar equations. And I think I am going to have to introduce the idea of a unit vector, but first, multiplication of vectors. Okay, there are actually the ones we're going to be interested in are multiplying vectors by scalars. And that's really the only one we're going to do. Now, remember, a scalar is just a number. It's something that has just a magnitude, but no direction to it. So things like that are scalars would be stuff like scalars. I'll make a little table of them. 3 or 5 or -2. Now, those are all scalars that have no units. I could also have something like 4 meters per second. That's a scalar. Or -8 meters per second, or -9.81 meters per second squared. Those are all scalars. And so we can just think of those as there's no direction to these things. I do happen to have minus signs on some of those, but without telling you which way is which, you don't know which direction these things happen to be pointing. So this happens to be the acceleration due to gravity, but it doesn't have to be. It could be the acceleration of a car when somebody tromps on the brakes, and we'll have that. But here's how multiplication by scalars works. Let's suppose I have a vector, A, that is this long and points in that direction. Okay, now, if I make a vector that is twice as long as that, this is what 2A will be. Okay, now this is assuming that the length of the arrow that I draw is representative of the magnitude of the vector. But when you multiply by a scalar like 2 or 3 or 5, all you do is increase the magnitude of the vector by that factor. Something else that happens here is that if I do this, that's a vector that points in the opposite direction with the same length. This is -1, and that'll be a 1, times A, or just -A. Okay, that's what the negative of a vector means. It has the same line that it acts along, it just points in the opposite direction. Now, with this idea, we can think about the subtraction of vectors, but we can also just deal with multiplying vectors and stuff like that. We're going to not so much deal with vector things. What we'll usually use is this particular property of vectors, and it's going to let us split things apart into an x part and a y part, and then solve scalar equations. But to do that, we need to use an idea of a unit vector. And this is a vector with a magnitude of 1, and it has no units by itself, even though we call it a unit vector. We call it a unit vector because it has 1 unit of magnitude and a direction and a direction. That's its only property. So here's some more abstract stuff. Once we start using these things, we're quickly going to just sort of go beyond here and not worry about it anymore. Now, here's some things about unit vectors. Suppose I introduce an XY coordinate system, and so y points up and x points sideways, and I introduce a unit vector that points in the x direction and one that points in the y direction. Now, in more advanced classes, what you'll usually use is I hat, j hat, and k hat for unit vectors. We're never going to use a k hat. In fact, I'm probably not going to use these in here. But the I hat points in the x direction. The j hat points in the y direction in these more advanced classes. And k hat points in the z direction. Okay, we're never going to use a third dimension, but if you were using that third dimension. Now, that's just one possibility of unit vectors that might be used. You can have different types of coordinate systems. The x and y and the z, if you added it onto there, are what are called the Cartesian coordinate system, named after René Descartes, who was a French mathematician. But there's also coordinate systems like a polar coordinate system that's more advantageous if you've got kind of cylindrical symmetry. There's spherical coordinate systems, all kinds of things that, and in those, each of those, you'd have different sets of coordinates that you might use. But for us, instead of using I hat for a unit vector in the x direction, we're going to use x hat. And instead of using j hat for a unit vector in the y direction, we're going to use y hat. And the way that we denote something as a unit vector is that we put a hat on it instead of an arrow. So unit vectors have hats. Okay. And that's the little caret symbol. And I figured out how to make hats in my equation solving software. And so I'll try to put them typed. But let's apply that idea to our idea for projectile motion, where we've got this initial velocity that makes an angle theta with the horizontal. And I'm going to split it into a v naught x and a v naught y, which are two vectors at right angles to each other. And so I'll have something like that. Now, v naught x, I could write as, remember we figured out that the magnitude of v naught x was v naught cosine of theta. I could write this as its magnitude times a unit vector in that direction. Okay, this x hat is just going to be something with a length of 1. When I multiply it by v naught x, it will become a vector that has a magnitude of v naught cosine theta, and it points in the x direction. V naught y is similarly going to be something that has a magnitude of y in the y hat direction. Okay. Now, this is kind of abstract and mathematical, but we'll try to bring it down to things that you're a little more familiar with as we go along here. Here's the thing with projectile motion. And this will be no air resistance projectile motion, so we'll ignore that. One thing is that v sub x is going to equal v naught x is going to be constant. There's no acceleration in the x direction. And another thing is that in the y direction, we can use free fall equations. Okay, now I'm going to show you just how scary the equations for this could be if I wrote them in 2 dimensions or using all vectors. Okay, they're going to look bad, but if it looks too frightening, put it out of your mind and we're going to simplify it almost immediately. But in 2 dimensions, we might describe the position of a particle in 2D, position of a particle is r is equal to x in the x hat direction. Okay, remember this is a unit vector. This is how far it would be in that direction, plus y in the y hat direction. Whoops. Yeah. By the way, at times I may slip into I hat and j hat. Just holler if I do. I mean to be using x hats and y hats here. So it's hard for me to resist the temptation because I usually teach this in the engineering physics class where we do use I hats and j hats. So we'll have that. R naught could be the initial position in the x direction plus the, whoops, this should be a y naught, initial position in the y direction, and so forth. And we already have an expression for v naught here. V naught I can write as v naught x along x hat plus v naught y along j, woo, y hat. It's hard to resist. Okay, now in general, if we have constant acceleration in 2 dimensions, here's what the equation can look like. It's going to look a little bit familiar. We could have that r, that's the position of the particle, will equal r naught for the particle plus v naught as a vector times t plus 1/2 the acceleration as a vector times t squared. Okay, now that's not so bad actually. It looks kind of like x equals x naught plus v naught t, v naught xt maybe, plus 1/2 at squared. Okay, it's the same form of the equation, but in 2 dimensions, there's 2 possibilities for this, 2 parts for this, 2 parts for this, 2 parts for this. And so you end up with an algebraic expression that has 2 terms on one side and 6 on the other, which is kind of scary. So let's see what that's going to look like. Let's see, I'll pull down a piece of scratch paper here for this part. I already told you kind of what R and R naught happen to be. Here's what it could look like in general, is that I could have X along X hat plus Y along Y hat, that's the R part on the left side, could equal X naught along X hat plus Y naught along Y hat. Okay, that's this part, plus V naught X along X hat plus V naught Y along Y hat. Yikes, this is getting bad. Plus 1/2 times A sub X T squared along X hat plus 1/2 times A sub Y T squared along Y hat. Okay, that is a frightening looking equation, but we're going to simplify it by a ton. For one thing, we're only going to apply this to projectile motion. And so here's something that we'll have. We'll have that A sub X is equal to 0. There's no acceleration in the X direction. That makes this term go away. Okay, it's 0. And A sub Y is going to equal minus G. That's going to turn that equation into minus 1/2 GT squared. And so I can do that with A sub X equaling 0. Let's see. Well, I lose one term that way. So here's what my horrible equation is going to become. It's still not a whole lot better, but it could be worse, and it was originally. That's going to equal X naught along X hat plus Y naught along Y hat plus V naught X along X hat plus V naught Y along Y hat minus 1/2 GT squared along Y hat. Okay, still a scary equation, but now I'm going to use that property of vectors, that if one vector equals another, then the X components on one side equal the X components on the other. And so I'll go along here, I'll just pick off the X components and set them equal to each other. Here I just have an X, so X is going to equal X naught, here's another X term, plus V naught X, and that's all. That's the X equation. The Y equation becomes this. Y is going to equal, I pick off the Y hat terms, Y naught plus, whoops, I forgot a T on these things. Yeah, they should have had T's on them, forgot. Anyway, need more. Anyway, plus V naught Y T minus 1/2 GT squared. Okay, this is one of our free fall equations. Okay, now I've just been dealing with the position equations for X and Y together, and so I get that, but I could also apply this to velocity equations, and for this I would get V sub X is going to equal V naught X. Going in the X direction, the velocity is a constant, and so I have a constant velocity in the X direction, which is not bad to deal with after you've dealt with acceleration, but the V sub Y equation ends up being V naught Y minus GT, okay? Well, we just finished a few days doing problems where we used these particular equations to figure stuff out. And so you've seen multiple examples of doing that. A projectile motion problem just happens to have, while the same time this stuff is going on, you've got something moving in the x direction with constant velocity. And so instead of something just going up and then coming down to the same position, you have something that's traveling along a path that's like this. But we'll analyze the two parts separately. The up and down we'll solve, and then we'll solve the x part, usually in that order too. So let's try some problems with that and see what we get. Let's see, I've used both sides of that one. Save it, but mostly you won't need it. Okay, where did I put the problems I printed off? This is a handout that I'll have, I'll upload it and make it available with today's stuff. But it starts off with a page of guidelines for solving a projectile motion problem, or solving a projectile motion problem. And something I do, as soon as I recognize that something's a projectile motion problem, I write down the appropriate equations. And I don't remember if I got these out of the book, your textbook, or if I wrote them on my own, but they're things that I've pretty much incorporated into the way that I do things. And then if I know the initial velocity of the projectile, given as the initial speed and angle, I can also write down v naught x is v naught cosine theta and v naught y is v naught sine theta. And usually I write them down without any numbers at first. And so my complete set of projectile motion equations are these ones, all 6 of these things. But I've got them kind of split into, well, I got the x and the y parts mixed up a little bit, but that's what they happen to be anyway. And then once I've written down those equations, I start identifying as many variables in the equations as I can. And often I'll be given the initial position. So much of the time you can set both x naught and y naught equal to 0, but not always. If something starts from ground level, I'll let y naught be 0 and I'll let x naught be 0. Nearly always x naught you can define to be 0. You'll usually be given the initial velocity. If not, maybe you might be given the initial x velocity or the initial y velocity. You'll usually be given the angle theta. If you're given v naught and theta, then you can figure these things out. And so you can calculate those, and then your equations start getting populated with things that you know. And so, and then from the problem description, identify what it is you're supposed to find. Sometimes you lose track of that because you've got so many things going on. Then look at the numbers you know, the equations you have, see if you can do it in a single step. If not, it may take a couple of steps to figure things out. So that's what we're going to be doing practice problems for, is to see just how that stuff works out. So let's try one. Okay. A projectile is launched at ground level with an initial speed of 50 meters per second and an angle of 30.0 degrees above the horizontal. Ah, this sounds like initial speed. That sounds like v naught to me. And this thing, 30 degrees above the horizontal, that's theta. Okay, so I recognize those things. It strikes a target above the ground 3 seconds later. What are the x and y distances from where the projectile was launched to where it lands? Now, who knows what the target was? It could have been, let's see, with a speed like that, somebody might have been practicing with a bow and arrow and aiming at some target that was a ways above them or something like that. Maybe they were standing in a trench and their arrow left the ground at ground level, because the trench was deep enough for them to have that be the case. Well, we can make a sketch. Never hurts to do that. So the thing is launched initially, and it's going to have some kind of travel like that. And this will be 3.00 seconds later. Okay, here's the initial position. Now, I didn't do something I'm supposed to do whenever I recognize that it's a projectile motion problem, and that is write down my equations. So I'll do that right now. And I'm going to write the y equations down one column and the x down another. So y is going to equal y naught plus v naught yt minus 1/2 gt squared. And v sub y is going to equal v naught y minus gt. And then y naught will, or v sub y naught, excuse me, v naught, or v naught y. I write them in varying orders. So v naught y will equal, or v sub y, no, I'm okay. Yeah, v naught y is what I want here. That's equal to v naught cos theta. So those are my y equations. Okay, x is simpler. X is equal to x naught plus v naught xt. V sub x is always just equal to v naught x because it doesn't change. It's constant. And v naught x is going to equal v naught cosine theta. And so those are my sets of equations. So for as many of the variables in the equations as I can, assign numbers from the descriptions of the problem. Okay, well, I'm going to let x naught and y naught both equal 0. Okay, so that's some simplification. I can say x naught equals 0, y naught equals 0. Okay, other things I can identify, v naught is 50.0 meters per second. Theta is 30.0 degrees. And so I may not use these numbers for a little while. I like to solve things in variable form first and then plug in the numbers. But I may as well figure out what v naught y and v naught x happen to be. Oh, this one's supposed to be sine theta. Did anybody catch that? V naught y is v naught sine theta. Well, let's figure out v naught y. That's going to equal 50.0 meters per second times the sine of 30.0 degrees, which I can do in my head. That's going to be 25.0 meters per second. How did I do that? Holy smoke, this guy must have all kinds of stuff memorized. I did it because it so happens that the sine of 30 degrees is exactly 1/2. And that's something that you learn when you take trigonometry. When I took trigonometry, first in high school, you could not buy a calculator at the time. The year I graduated from high school, the first handheld calculators came out. And the first ones did about as much as a TI-30X does. Really primitive. They had multiplication, division, addition, subtraction. They could calculate logarithms, and they had sine, cosine, and tangent. And they cost $400. My minimum wage janitor job paid $2.15 an hour. And so I wasn't going to be buying a calculator anyway, not on that wage, but I dropped out of college shortly after that. And by the time I went back taking math classes, you could buy a TI-30 for 10 bucks. So then I bought a calculator. All right, so the other thing, v naught x, this one I can't do in my head, is going to be 50.0 meters per second times the cosine of 30 degrees. calculations like this are what calculators are good for. So 50 times the cosine of 30. And it's, oh great, 25 square roots of 3. I don't care about square roots of 3, but I can get it to be a number. It's 43.3 meters per second. Okay, so I know those two. Now, what are my equations going to look like with these things defined? For instance, the y equation. Y is going to be, it's usually y naught, well it is, y naught plus v naught yt minus 1/2 gt squared. Y naught is 0, so it simplifies to v naught y times t minus 1/2 gt squared. The x equation, which is usually x naught plus v naught xt, I decided to make x naught 0, and so this is just going to be v naught x times t. Okay, well that's easy. And I have numbers for v naught x and v naught y, and this question is a good one to start with because all they want are the x and y distances from where the projectile was launched to where it lands. Okay, now, as far as landing goes, I don't know that it's actually going to be on land. I think it's going to be something that's above ground level, but let's find out. After 3 seconds, after 3.00 seconds, I think, yes, y will equal, well, I'm going to put in the numbers now. V naught y is 25.0 meters per second. And for t, I'm putting in 3.00 seconds minus 1/2 times 9.81 meters per second squared times 3.00 seconds squared. I just translated this into numbers. And so after 3 seconds, this is going to be the value of y. 25 times 3 minus 0.5 times 9.81 times 3 squared. And I get, let's see, 30.9 meters. So it's going to be up on top of something 30.9 meters high. That's actually pretty tall. That's about 100 feet high. So, oh, maybe they were attacking a castle. That's it. And these are the archers who are doing that. And then the x equation is just v naught xt. Well, v naught x is 43.3 meters per second times 3.00 seconds. So that's going to be a ways. I know what's going on. These people are making a Robin Hood movie. And so that's what we're looking at. Yeah, and I get, let's see, to 3 significant figures, I could write it 1.30 times 10 squared meters. If I just write 130 meters, you don't know how many significant figures I've got. But if I write 1.30 times 10 squared meters, you know that it is. And so, yeah, these are those archers with the longbows in a Robin Hood movie. And this was way up in the tower of the castle they're attacking or something like that, to be that high off the ground. So we just solved our first projectile motion problem. And let's see what the next one looks like. Any questions about what I did on this, other than scribbling out a whole bunch of stuff? Let's see what else we might get. Soccer player. Okay, kicks the ball with an initial velocity of 16 meters per second in the horizontal direction and 12 meters per second in the vertical direction. Okay, at what speed does the ball hit the ground? And for how long does the ball remain in the air? Huh. Well, there's lots of questions here. But soccer balls behave like projectiles, and so I can write down my projectile motion equations, which look like y equals y naught plus v naught y t minus 1/2 gt squared. V sub y equals v naught y minus gt. Let's see, that should do for that one. And v naught y equals v naught sine theta. So those are my usual y equations. And for x, it's just x equals x naught plus v naught x times t. And v sub x equals v naught x. No change in that one. So, oh, and v naught x is x equals x naught plus v naught xt. V naught x is equal to v naught cosine of theta. Okay, well, there seems like there's a lot of missing parts of this problem. However, initial velocity of 16 meters per second in the horizontal direction, that's v naught x. So this thing I happen to know. Okay. And 12 meters per second in the vertical direction, that's v naught y. So, and maybe I don't even need to know the angle that it's kicked at or anything like that. I can figure out the initial speed, and the way I can do that is using something called the Pythagorean Theorem, that because this is v naught x going this way and v naught y going this way, and this is just the scalars of them. This is v naught, and the initial speed of this thing, v naught, is going to be the square root of v naught x squared plus v naught y squared. I may not need this, but I can figure it out in this case. So I'll just plug them into my calculator. 16 meters per second and 12 meters per second. I think it's going to be 20 meters per second, because this happens to be 3 times 4, and this is 4 times 4. And that would make this thing a 3, 4, 5 right triangle, if you happen to remember what those are, but we'll just check and make sure. The square root of 12 squared, wherever it is, there's the squared button, plus 16 squared is equal to 20. Yes, so this will be 20 meters per second. And I'm going to put a little note to myself here, 2 significant figures, because 12 has 2 significant figures and 16 has 2 significant figures, and that's all I've got to deal with on this problem. So how am I supposed to solve this thing? Well, I'm going to make myself a little sketch here. I'm going to make an assumption. They didn't tell me for sure, but I'm guessing that the soccer player kicked the ball off the ground level. And so maybe it was one of those things they do in soccer where they do that. And so I'm going to let x naught and y naught equal 0 there. Okay, and then, well, looks to me like y final down here, y is going to equal 0 when it comes back to the ground. They usually make soccer fields level. So that's something that I happen to know, because I used to do, well, I played football, and that was usually on a level field, except at Hastings. They had the weirdest field in the world. But that was a high school that we played in 10th grade football. All right, now at what speed does the ball hit the ground? Well, if I want to know that, I have to figure out first how long the ball is in the air, which I can do using my y equation here. And once I know that, I'll take the time that I get and plug it into this equation, and I'll know how fast, or at least its velocity in the y direction is when it comes back to the ground. The velocity in the x direction is always 16 meters per second. But in order to be able to figure this one out, I need to know how long it's in the air. And that depends on when this thing is equal to 0. But this equation changes into y is equal to y naught, which is 0. I'll write it down here. V naught yt minus 1/2 gt squared, which with the numbers plugged in will be V naught y is 12 meters per second times t minus 1/2 times 9.81 meters per second squared times t squared. When is that equal to 0? Okay. Now, this could be a scary looking quadratic equation here, except that it's not. Actually, I'm going to leave it in letter form first and set that equal to 0. V naught y t minus 1/2 gt squared is equal to 0. Okay, if this was a full quadratic equation with a y naught sitting over here, I'd have to use the quadratic formula, but I can factor this. Both terms have a t in it. And so if I factor that out, I'll have t times v naught y minus 1/2 gt is equal to 0. And something you learned in algebra, if you have two numbers multiplied together that equal 0, either this one can be 0 or this one can be 0. Well, one of the answers I get then is t equals 0. That makes sense. That was the time when it was kicked off the ground. So of course y was equal to 0 then. Right? The other one though is v naught y minus 1/2 gt is equal to 0. And you can solve this for t. V naught y equals 1/2 gt. Multiply both sides by 2 and divide by g, and you would get 2 v naught y over g is equal to t. This is something important. If you have a projectile that begins and ends at the same height, its time of flight is going to be twice the initial velocity in the y direction divided by g. So that's good to know. Okay, well, now that we know that time of flight, we could actually punch numbers here and get it. 2 times, where is v naught y? 12 meters per second divided by 9.81 meters per second squared. Unit-wise, I'm going to do that on scratch paper. Some of you probably know this already, but meters per second divided by meters per second squared, flip and multiply, and you get meters per second times second squared over meters. Meters divide out. One of the seconds here divides with that one, and you just get seconds. Okay, that's good for a time of flight. And the number I get for that time, 2 times 12 divided by 9.81, and I don't have my calculator on, so that won't help. There we go. I get about 2.4 seconds for the time of flight of this soccer ball. All right, well, that's just how long it's in the air. What was the question? Oh, at what speed does it hit the ground? Okay, so for part A, which I'm still working on, I know how long it's in the air. I can use my v sub y equation to figure out how fast it's going when it hits the ground now, or its y velocity. V sub y will equal v naught y minus gt, which is going to equal 12 meters per second. They gave me that, minus 2.4 seconds times, that was the t, times 9.81 meters per second. Oh, and I'll show you meters per second squared. I'll show you something here in a minute. V sub y, when it hits the ground, is going to equal 12 minus 2.4 times 9.81. And to two significant figures, I get minus 12 meters per second, which I kind of knew. Let me show you something. We figured out that the time of flight of that thing was 2 v naught y over g. And v sub y is equal to v naught y minus g times 2 v naught y divided by g. That was the time of flight. And this becomes v naught y minus 2 v naught y, which is minus v naught y. Oh, okay. So when it hits the ground, its upward velocity is the same as, or its downward velocity is the same as what its upward velocity was to begin with. There's a kind of symmetry to this. And the total velocity when it hits the ground is going to be the square root of v sub x squared, which is constant, plus v sub y squared. And so it'll be that square root of v sub x was 16 meters per second squared plus minus 12 meters per second squared. And it'll end up being 20 meters per second, two sig figs again. And its speed when it hits the ground is exactly the same as the speed when it left it, as long as we can ignore air resistance. So that's something that comes out of our equations. With no air resistance, or if you could do this on the moon, you could kick a soccer ball on the moon. One of the Apollo astronauts took along a golf club and a golf ball and hit the golf ball on the moon. So why not? It works. It goes farther on the moon. We'll see that in a little bit. But anyway, there's our first couple of problems there. We didn't figure out we did figure out how long it remained in the air, 2.4 seconds, but we didn't figure out the maximum height attained by the ball. And so that may be something that we can mess around with later. So, but we'll stop there for today and see how things go anyway. Any questions on that? We did quite a bit today. I'll get this posted up there. And going forward, when we're doing the projectile motion things, we're probably not going to worry about those X and Y components very much, although we will be thinking about those some when we get to forces and stuff like that, at least the vector nature of it. But from here on out, when we're doing projectile motion problems, we'll just write down those equations right at the start of the solution and then see what we can do with them. And they'll all be scalar equations that we're dealing with. We'll think about the fact that there's motion in two directions, but we won't have to mess around with it too much.
You were talking about a lab that's coming up at some point.
Yeah, I'll be posting that later today. I've got the video and the lab printed off and the data gathered. I just have to collect it together into a single page on here.
Oh yeah.
Yeah. But it's one, you don't have, it's not a live in-person lab or anything. You'll just take the data that I gathered and deal with it that way. And it's not a very hard lab at this point. So simpler than the stuff we've been doing in class anyway. I hope. You will need a partner for part of it. You'll be determining your reaction time. And so you'll need someone to drop a ruler for you. So, but I'll show you what that is in the video that I've got with it. Anyway, have good weekends if I don't hear from you otherwise.